What is going on, guys? My name is Amos and I'm back with another video. So in today's video we want to talk about reduction formulae. So I'm going to make the assumption that you guys are already familiar with what is known as integration by parts, and you've at least tried to solve some problem or where you apply the integration by parts. Now here in this video, we want to talk about developing what is known as a recurrence relation, because integration by parts becomes tedious for some functions. That is because you have to do it a couple of times. For example, 2 times, 3 times, depending on the function that you have. You're going to do it many times. So if you have something that is known as a recurrence relation, you can find the values of you can evaluate any integral that is taking different values of n. So that is what we want to achieve today, and I'm going to propose three problems to you, and let's get started. So the first problem is the integral of x to the power of n e to the power of x dx. Now integration by parts here becomes very tedious. So for n equal to 2, you have to do the integration by parts 2 times. For n equal to 3, you probably have to do it for 3 times. For n equal to 100, you have to do it for, I don't know, like 100 times. So that is very tedious. All right. So let's develop what is known as the recurrence relation. From that recurrence relation, we can find the values. We can evaluate different integrals, that is taking different values of n. So we're going to start by, we're going to develop that recurrence relation using what is known as integration by parts. Great. So now this is the formula for integration by parts, that is u v prime. This is going to be equal to u v minus u prime v. So this is the formula of we're going to use for our integration by parts. Now in this case, u and v are two functions. U and v are functions that are differentiable at least once. Great. So u and v are two functions that are differentiable at least once. Functions, so let me just write that here, functions that are differentiable at least once. Oh, great. So let's solve this problem. All right, so we have to choose what is going to be our u and what is going to be our v prime. So let me just write it again. I think we lost it. So x to the power of n e to the power of x dx. So we're going to say let u be equal to x to the power of n, and we let v prime, so u v prime, we let v prime be equal to the power, be equal to e to the power of x dx. All right. Now we are going to find u prime. U prime is equal to, now it's the derivative of x to the power of n. So the derivative of x to the power of n is n x to the power n minus 1. And here we have to find the integral of v prime. That is going to be v. Now we know that the integral of e to the power of x is e to the power of x. Great. Now this means that the integral of x to the power of n e to the power of x dx is going to be equal to, what is our u? Our u is x to the power of n. What is our v? Our v is e to the power of x minus the integral of, what is our u prime? Our u prime is n x to the power of n minus 1. Now what is our v? Our v is e to the power of x. Great. Now x to the power of n e to the power of x. Now the n is the constant. N is a constant because here we are integrating with respect to x dx. So n does not depend on x, so we can take it out of the integral sign. So we can have the integral of x to the power of n minus 1 e to the power of x dx. Now if you compare this to, if we let this be equal to in, if you compare this to this, notice that here n has decreased by 1. So we have n here we have n minus 1. By comparison, we get that in is going to be equal to x to the power of n e to the power of x minus n e to the power n minus 1. So This means that now you have developed your recurrence relation. So in is equal to x to the power of n e to the power of x minus n e n minus 1. Now let's see how we can use this recurrence relation to solve one quick problem. Now let's take n as 2. Let's see how this recurrence relation is going to help us. All right, so let's pause n as 2. So if n is equal to 2, we're going to have I of 2 is equal to the integral of x to the power of 2 e to the power of x d dx. Now that looks great. So now we need to evaluate this. How do we evaluate this? So we use our recurrence relation. The recurrence relation is in is equal to x to the power of n e to the power of x minus n I n minus 1. Let me just take care of the bottom part to give ourselves enough room. So n is equal to 2. Therefore, I of 2 is going to be equal to x to the power of 2 e to the power of x minus now 2i. Now what is our 2 here? What is our n? Our n is 2. So 2 minus 1 is 1. So we also have to find I of 1. Now how do we find I of 1? It's very simple. We use the same recurrence relation. So we know that I of 1 is going to be equal to x to the power of n e to the power of x minus n is 1. N is 1. So we're going to have I0. Now what is I of 0? We use the same recurrence relation. So I of 0, now here we have to be careful. N is in the set of natural numbers. So I'm going to put a star here because n doesn't have to be 0. N doesn't have to be 0. So we're going to start from 1 and so on and so forth, and so on and so forth. So I of 0 it's easy to find I of 0. You just look at your integral. So you're going to say or, but here I of 0, let me just wrap this. I of 0 is going to be equal to, now it is x to the power of 0, which is 1. So we're going to have e to the power of x d dx. Now the integral of this is e to the power of x. So I'm going to have that I of 1 is going to be equal to x to the power of n e to the power of x minus I of 0, which is e to the power of x. Now that looks good. So after finding I of 1, we have to, now the goal is to find I of 2. So we go back here. So we're going to replace I of 1 here. So we have that I of 2 is going to be equal to x squared e to the power of x minus 2. What is I of 1? I of 1 is x to the power of n e to the power of x minus e to the power of x. Now let me just take care of the bottom part to give ourselves enough room. So I of 2 is going to be equal to x to the power of 2. Now that does not look good. Now that is x to the power of 2 e to the power of x. Now minus 2 x to the power of n e to the power of x plus minus 2 minus e to the power of x. So that is plus 2 e to the power of x. So we can factorize by e to the power of x. So we have that e to the power of x is equal to x to the power of 2 minus 2 to the power of wait, so this is 1, so this has to be 1. Remember this was for I1. Let me just reduce the size of this guy. So this has to be 1. I forgot to substitute, so this has to be x. Remember this was we got this from I1, so this has to be 1. So let me just correct that here, and this is the only place I have to do that. So we are good to go. So this has to be x. Now plus 2. Now here is your I2. So I2 is equal to e to the power of x. Now we have x squared minus 2x plus 2. This is your I2. Notice how easy that was. Though it was a little bit lengthy because we had to find I0 and I1, but the process was easier. So that's how you can use your recurrence relation. Now let's look at another recurrence relation. So same formula. Great. So let's get Let me just take care of this. We are done with this. So let's look at in is equal to the integral of x to the power of n cosine of x. Cosine of x dx. Now, how are you going to find the recurrence relation? Same procedure. We have to use integration by parts. So let me just say integration by parts. Now, just some abbreviation here, integration by parts. So we have to choose our u. Our u is x to the power of n. We have to choose our v prime. Our v prime is cosine of x. What is our u prime? Our u prime is n x to the power n minus 1. Now, what is our v prime? What is our v? Our v prime is cosine of x, so we have to find our v. Now, v is the integral of cosine of x. So v, the integral of cosine of x, is sine of x. So let's now find the recurrence relation. We know that I of n is going to be equal to, now what is our u? Our u is x to the power of n. What is our v? Our v is sine of x. Great. Minus the integral of, what is our u prime? Our u prime is n x to the power n minus 1. Now, like in the previous problem, n is a constant. It does not depend on x because we are integrating with respect to x. So we can take it out of the integral sign. So we're going to have x to the power n minus 1. Now, what is our v? Our v is sine of x. Our v is sine of x. Great. Now, if you look at this and you look at I of n, notice the difference here. Quite all right. The n has, we have that n has decreased by 1 because we have x to the power of n here and x to the power n minus 1. But here we have cosine of x. Here we have sine of x. So this means that we have to do integration. We have to do the integration by parts again on this side here. So I'm just going to let this be equal to j of n. Now, let's integrate this by parts. So that looks good. So let me write it here. So j of n is equal to, so let me just use this part that is here to find our u. Now, in this case, what is our u? Our u is going to be x to the power of n. X to the power of n minus 1. Now, what is our u prime? Simple. It is n minus 1, x, n minus 2. Now, what is our v prime? Our v prime is sine of x. Great. Now, this is our v prime. Let me just put that there. And what is our v? It is the integral of sine of x, which is minus cosine of x. Now, that looks good. So, what is our u? If we use the formula, our u is x to the power n minus 1. And what is our v? Our v is minus cosine of x. Great. Now, that is minus cosine of x minus the integral of u prime v. Now, what is our u prime? It is n minus 1 x to the power n minus 2. Now, n minus 1, like in the previous problem, is a constant. So we can take it out of the integral sign. This has to leave us with x to the power n minus 2, which looks good. Now, what is our v? Our v is minus cosine of x. So we can take out minus 1, such that here we're going to have a plus. And then we're going to have cosine of x. This means that j of n is going to be equal to, now if you compare this to our problem, to our I of n, notice that this is going to be in of 2. This is going to be in of n minus 2, not in of 2, but in of n minus 2, because n has reduced by 2. So this is going to be x n minus 1. Now this is going to be cosine of x plus n minus 1 n minus 2. Now let's resubstitute. So we go back to this stage here. So let me just take care of this top part to give ourselves enough room. Great. So I of n has to be equal to, now this part is going to be here, x to the power of n sine of x. Now it is minus of n multiplied by j of n. So minus n multiplied by minus x to the power n minus 1 cosine of x. That has to be plus n x to the power n minus 1 cosine of x, and minus n multiplied by positive n minus 1, the integral of x to the power n minus 2 cosine of x, which is otherwise n minus 1 in minus 2. So this has to be minus n, great, and then n minus 1 in minus 2. Now let me just verify that that is indeed the correct recurrence relation. So we have x to the power of n, great, sine of x plus n, x to the power n minus 1 cosine of x plus, great, great. So that looks good. So we have that n minus 1 in minus 2. Now let me just take care of this part. Oh, right. So we have minus n. Yes, indeed, this is the correct recurrence relation. So we have x to the power of n one more time, sine of x plus n, x to the power n minus 1 cosine of x minus n minus 1 in minus 2. Now you have your recurrence relation. So for n equals to 2, you can solve your integral easily, like we did in the previous problem. So now, without any example, we go to another problem, to another recurrence relation. Now I didn't have to rub the formula for the for integration by parts, but anyway, you already know it. So let's look at another problem. Great. So let's look at the integral of x to the power of n sine of x dx. All right. We have to choose our u. What is our u? Our u is x to the power of n. Now, what is our v prime? Our v prime is sine of x dx. What is our u prime? Our u prime is n x to the power n minus 1. And what is our v? V is the integral of sine x, which is minus cosine of x. Great. Now, the integral, now this is our in. This means that in is equal to, now what is our u? Our u is x to the power of n. What is our v? Our v is minus cosine of x. So minus cosine of x minus the integral of, that is u prime, and like in the previous problems, is going to be a constant. So we're going to take it out of the integral sign. So that is going to be x to the power n minus 1 multiplied by v, which is cosine of x. Now minus cosine of x, which is minus cosine of x here, but minus, if we take out the minus 1, we're going to have plus here. Okay. Now, if you make your comparison, quite all right here, we have that x in x is raised to the power of n. Here x is raised to the power n minus 1. Now here we have sine of x. Here we have cosine of x. So to get that sine of x, we have to do the integration by parts one more time. All right. Now I'm going to let this be equal to j of n, the integral of x to the power n minus 1 cosine of x. So let's say j of n is equal to the integral of x to the power n minus 1 cosine of x. Now here we have to choose our u and all those good things. So let me just take care of the top parts to give ourselves enough room. So what is going to be our u? Our u is going to be x to the power n minus 1. Now don't look at this, but look at this that is down here. It's a little bit confusing, but yeah, we just have to get used to it. So we have u is equal to x to the power n minus 1, and we have v prime is equal to cosine of x dx. Now our u prime is n minus 1 x to the power n minus 2. Now I'm just going to do that. And our v is the integral of cosine of x, which is sine of x. Now that looks good. And this means that j of n is equal to, what is our u? That is x to the power n minus 1. Then what is our v? Sine of x. Great. Now minus the integral of u prime. N minus 1, like in the previous problems, is a constant. So we take it out of the integral sign. Then we're going to have x n minus 2. Now, what is our v? Our v is sine of x. Boom. we have our sine of x. Now, if you compare it to I of n, we have that j of n is equal to x to the power n minus 1 sine of x minus n minus 1. Now, this is I n minus 2. Now, let me just take care of the top part to give ourselves enough room. Great. So now, what is our I of n? Our I of n is going to be equal to, now it is positive n. It is positive n multiplied by j of n. So this guy is going to be here, x to the power of n cosine of x. Now, positive n multiplied by this is going to be x n. Let me just take care of that. Plus n x to the power n minus 1 sine of x, and positive n multiplied by that is going to be minus n n minus 1 I n minus 2. So that is what we have for our recurrence relation. So now I can just take care of everything. And we just have to verify that this is the correct recurrence relation. Minus x to the power n cosine of x plus n x to the power n minus 1 sine of x minus n n minus 1 I n minus 2. Great. Now everything can go, and thank you guys for watching, and I'll see you in the next video. Be sure to subscribe and hit the like button if you like the video. Thank you.